All right, so we're here with you guys for the second half of our 2.2 module. We're taking a look at, or continue to take a look at how DNA replicates itself. So here is about roughly where we left off. And the last thing we put down there is a notice of how one of the primases can follow directly behind the helicase as he unzips the DNA. And the other primase is moving away from that helicase. And so that's what we're going to pick up now. That leaves us with two strands of DNA. We call the first one the leading strand. And the reason we call it the leading strand is because it's able to just follow directly behind the helicase as it unzips more and more DNA. It's going to be out in front. It's constantly going to be copying DNA faster than the other strand can. Back to our drawing here. And honestly, we don't care too much about this one. Just kind of have a dot, 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 because again, we just don't care about this bottom strand. That's going to be what we call the lagging strand. And we'll get back and take a look at him a little bit later. So again, the bottom one here is going to be our lagging strand. But for right now, we're concentrating on the top one, which is the leading strand. It doesn't necessarily have to be the top one. What's important, though, is that it is the 3' to 5' end, because the strand we're going to build is going to be 5' to 3'. So the opposite of the 5' here. So we still have our little helicase in there, still working away and zipping the DNA. We'll even add some SSBPs. They haven't gone anywhere. But right here, I'm going to draw my circle. If you guys remember from the first half of the notes, the circle represents DNA polymerase. And it's his job to add nucleotides. So throw a couple nucleotides around here. They're just kind of floating around. Sometimes they get brought in and they start to get paired up. With the DNA. So we're kind of following behind, and he's been building all of these. We started down here and he's moving in this direction directly behind helicase. Now right here with a couple of nucleotides left, I'm going to add my blue, because remember, this is a primer. We needed that primer. It's an RNA primer. That's why it's a different color. We needed that primer. There we go. We needed that primer because, again, DNA polymerase can't get started on his own. He needs a little bit of help from his friend. We saw that up here. The RNA polymerase, which is a primase. We need that to get us started, but it builds, when it gets us started, it builds this blue or RNA. It's different than DNA. So little different colors. We kind of see, hey, we're not working with DNA on this particular end right here. And then again, important to note, it is building these strands 5' to 3'. He is reading that strand up top there. He's reading that 3' to 5', but he's adding nucleotides 5' to 3'. Drop the pin there. All right, so this is what we call the leading strand. And here's our note on this guy. So once that primer has been established, DNA polymerase, that's a big circle, is able to continuously add complementary nucleotides. And again, what that means, complementary, whenever he reads a T, when the parent strand has a T, he brings over an A. When the parent strand has an A, he brings over a T. When the parent strand has a G, he brings over a C. So those are our complementary nucleotides that just bring it over, and he builds and he adds onto the strand, and that's that. He just kind of goes as helicase continues to unzip more and more DNA, he just follows right behind him, making more and more DNA. The leading strand, really pretty simple. And that's all I've got for the leading strands. Let's flip the page here. I need to start a new page. For my lagging strand. So next up, we have the lagging strand. And it's so named. We saw the leading strand. Leading strand is going to be out in the lead. He's going to be building nucleotides as soon as the DNA is opened up. But the lagging strand lags behind. We're going to have big open stretches. You'll see that hopefully in a second here. We're going to have these big open stretches of DNA where it's been unzipped, but because we're working away from helicase, we haven't paired it up. So it lags behind in the process. So for the most part, we're drawing the same structure. I'm gonna go all the way across though. We'll need a little bit more room for this one. But otherwise, we're drawing pretty much the same exact structure we just worked with. Except on this one, it's the top strand we don't care about. So it can just kind of fade away into the distance there. This time we care about this bottom strand. And we took a look at the top strand on the last one. And now we're looking at the bottom strand. Not that it's important which one's on top and which one's on bottom. You can flip them very easily, and that's absolutely fine if you do so. The important part is that down here is the 5'. You can follow that up. The 3' then is right here. That's the other end of this strand. Makes this the 5', and the 3' is going to fade off in the distance there. Again, we're not worried about that. That is our leading strand. But right now we're looking at the lagging strand. Okay, so we still have our helicase. He's still there. He's still opening up the DNA. Can add a couple of SSBPs. And I'm going to go ahead and add a primer here. So the primer got started right here. And right next to that then, I'm going to add our DNA polymerase. So here's our DNA polymerase. And again, he's adding those nucleotides, have some flying around. They're coming, they're getting to work with them. They're getting in there, and as he reads the DNA, he adds the corresponding, the complementary nucleotides, and he builds a strand. Again, he needed this primer, though, to get started as he's building. Now, as you can imagine, so imagine with me here, helicase continues into the future. We're going to have a big open stretch of DNA that's not currently being copied. We'll get to it eventually, but it's not currently being copied. Well, what if we rewind? What if we twist this back up? We take these primases off. They haven't happened yet. The helicase comes back here to where we first unzip this particular area. You with me? So we rewound, and we're back to here. Well, back when we were unzipping down here, we had pretty much the same exact thing happen, except down here then, we already made that primer, and we've already got DNA polymerase going. So we're kind of looking back in the past here. I'm going to add another primer. A different color, because those primers are made of RNA. And then I've got this other strand of nucleotides. Make sure that one connects up. And this guy, man, he's been at work for quite a while here. So it's another DNA polymerase. And again, he's adding in those T nucleotides are coming in. And at the end of this one, I'm going to say imagine this guy, as he keeps going, eventually he's going to run into this primer. Well, I'm going to say this guy's been going so long, he's already run into the primer ahead of him. And actually, I'm going to start kicking off some little blue T's. So my black T's are going in. My blue T's are getting kicked off. We'll kind of come back and discuss that in notes in just a second here. So what we're building, this guy's getting ready to complete one. This guy's just starting one. Again, he's further along in time than this guy. He started getting to work when we were still zipped up down here, and the helicase moved this way, opened up more, and voila, this guy could get to work. Well, what we're looking at is this little fragment that we call an Okazaki fragment. Okazaki fragment. You'll see soon here, it really is a fragment. It really is a piece of DNA. In fact, we kind of have to fix it once we're all done. So they're named after the man who discovered them, Dr. Okazaki. And we've got these just, again, fragments or pieces of DNA. All right, so let's take a look at the terminology and see what's going on here. Take a couple notes on it. So the lagging strand is constantly having to make new primers. Here's a primer. Here's a primer. We're running into a primer right there. As we continue to unzip the DNA in this direction, we're going to have to put another primer down here somewhere. So as we open up more and more DNA, we're constantly having to make more and more primers. If you remember the leading strand, we just had to make one primer, and then that DNA polymerase could just follow right behind helicase as he opened up the DNA. All right, so there's our term Okazaki fragments. So again, what this leads to is we have these stretches of DNA on the lagging strand. Again, if you think about the leading strand, it's really just going to be one continuous piece of DNA because you can just follow right behind the helicase. But the lagging strand, you're going to have all these different chunks of DNA, all these different fragments. They're usually 100 to 200 nucleotides long. So ours are not long enough. What's fine? Maybe 20. So yeah, we got about 10 times the length if we really want to make it accurate, but we're not going to draw that many DNA base pairs. So 1 to 200 nucleotides long, and again, they're called Okazaki fragments. Finally, what we see going on right here as this DNA polymerase runs into the next primer. So last little note here about what we're seeing occurring right here. When that DNA polymerase reaches another primer. He's going to kick off those RNA nucleotides and add in some new DNA nucleotides. So he's replacing the RNA. Hey, we're getting rid of it. We're solving one problem right there. We don't need that primer anymore. But we do have a problem. We do have an issue. So this all looks pretty good. We're solving all the problems we had, but here is our last little problem. You can kind of play fast forward in your mind here. This RNA polymerase is moving along. He's adding nucleotides. He starts kicking off RNA molecules. RNA, it's getting kicked off. RNA is getting kicked off. RNA is getting kicked off until he reaches right here where the DNA is. So when this Okazaki fragment started, there he's going to have a problem. Here's what that problem is. So imagine again, these blue nucleotides get kicked off, and I'm going to kind of enlarge, not by much, but I'm going to enlarge just this segment right here. We're focusing right there in about 10 seconds from now. Once this guy gets up there, that's where we're going to be looking. So again, I've enlarged this part right here. So in the bottom here, we have the 5 prime. And this is the template strand. This is the strand he's reading. And this is the strand he's building. And we're all fine and well and good, except right here. Right here, we've got an issue. Our DNA polymerase can't connect 3 prime to 5 prime. So this becomes kind of an issue. This is where that other weakness comes into play. We can't connect this strand. Doesn't matter if it's the leading strand or the lagging strand, we run into this issue. Now it'll happen more often on the lagging strand, because it's constantly running into primers, but it does happen on the leading strand as well. And the problem we have is that DNA polymerase can't. In bold, he just cannot do it. He just can't do it. He can't connect 3 prime to 5 prime. It can't be done. So we've got the strand here. He can't build it backwards and link these two together. He can only add nucleotides to this end. So we've kind of got this gap or this hole in our double helix, and that can be quite problematic. And that's what we're referring to right here. Our DNA would not be very strong here. It'd be very, very susceptible to breaking in half. And you do not want a broken in half chromosome. That can be dangerous in a lot of different ways. So we need a way to fix this. Thank goodness. For us, we have, I'm going to put these as dotted lines here. So this is where the hole was. It's being fixed. Thank goodness for us, we have our final enzyme that we haven't looked at yet. And that's the oval that we call ligase. So our final enzyme here, ligase, is going to come in and he gets to do his job. So ligase is able to do his job and bridge that final graph, is able to connect 3' to 5'. And so we can link up all of our different segments. Again, it doesn't matter if it's a leading strand or lagging strand, they all run into this problem eventually. Happens a lot more often on the lagging strand, but thank goodness for ligase, who can come in and just kind of glue those two together, can form that phosphodiester linkage and make sure that we have our DNA as strong as it possibly can be. All right, well, I think that wraps up the notes on DNA replication. Make sure you guys are reading through the packet before the homework as well. A little additional information there. But hopefully it's helped, and come talk to you during a pathways, especially if it didn't. And let me know what you guys think of the music. As you guys watching the video, thumbs up, thumbs down, whatever it happens to be. Let me know. Continue it or discontinue it based on what you guys are thinking. But otherwise, I'll see you later.